Okay, so today we will discuss creep. So what is the definition of creep? It is the time dependent deformation at high temperatures when the applied stress is well below yield strength. So generally we see this type of curve. We have this creep strain and here it is time. Okay, so this transient region, this we consider as the first stage. Three distinct regions we can see. So what is first stage? Decreasing strain rate. The slope of the curve d epsilon by dt, it decreases in the first region. Second state we call steady state creep. Here the slope is constant, almost constant. So that was strain versus time. If we plot strain rate versus time, suppose we plot creep strain rate versus time, we get a curve. First there is decreasing strain like this, then it will go something like constant, then it will again increase. So here it is the region 1, region 2 and region 3. Similar with the case if we plot strain rate, this is creep strain rate, same as this, versus time, we get this kind of curve again. It will be almost constant and then these three regions. So why this happens? This creep curve is a resultant of two factors, two processes going on simultaneously. One is recovery, second one is strain hardening. So these two processes are applicable only for stage 1 and 2, not to stage 3. Why I will discuss. So in stage 1, rate of strain hardening is greater than the rate of recovery. That's why we see a pattern like this. Initially, this is for stage 1. Then what happens in stage 2? Both rate are same. That is, rate of strain hardening is equal to rate of recovery. That's why we see a constant slope. This region. And in stage 3, what happens? Due to these processes, there is void formation. So because of this creep defect formation, what happens? This is not applicable and the strain increases this region. This is stage 3. So because of creep void formation of the grain boundaries and other defects formation, so the strain rate increases very high rate in the 3rd stage. Is it clear? Because of what? Necking and void formation. So that's why we do not consider this as a competition between strain hardening and recovery for stage 3. And also all kind of metallurgical changes like, for example, coarsening of precipitates, recrystallization, and diffusional changes. All these things occur during the tertiary stage. And one more important point is, what is the difference between constant load and constant stress creep test? Okay, so suppose this is the curve for constant stress. So how will be the curve for constant load? Will it to the left side or to the right side? So that will be something like this. This is for constant load. So the failure time will be smaller as compared to constant load. Why? Because in constant stress, that constantly updates the load divided by area. So the load is adjusted so that the stress remains constant. But here what happens? The load is constant. So continuously with decrease in cross-section area, decreases. So stress gradually increases. Even if the load is constant. So that's why it fails rapidly as compared to constant stress test. Okay, is it clear? So what is the most important parameter in creep test? That is the grain size. We know the Hall patch relation, yield strength equal to sigma y, sigma 0 k by root t. This is the grain size or grain diameter. So we have a term called equicohesive temperature. What is this equicohesive temperature? Do you know? So it is the temperature at which the strength of grain boundary is equal to strength of the interior of the grain. Okay, so when temperature is less than T equicohesive, it implies that grain boundary is strong. When temperature less than T equicohesive, when temperature greater than T equicohesive, grain boundary is weak. And why this grain boundary becomes weak at high temperature is because grain boundary has more random structure. Suppose this is interior of one grain and this is for other grain. So this is the grain boundary, this region. So there are a lot of open spaces. So what happens? Diffusion becomes easier when there is a slight increase in temperature. So that's why as we go on increasing temperature, so these become the easy diffusion paths. So these become weaker. So grain boundary sliding takes place and these become weaker. So we can say creep strain rate is directly proportional to grain diameter to the power minus p. So what is this p? Which is grain size exponent. So the overall strain rate we can write this is an important relation. This is the grain size exponent, this is the stress exponent, this is the activation energy. So P and N both are required to determine the mechanism of creep. Clear till now?
Sir, like in this equation, the strain rate is like it is directly proportional to d to the power minus p.
Yes.
So this grain size has a negative power. So means whatever be the mechanism, like it is a principal rule that fine grain sized material will have lower creep resistance.
No, fine grain material. Yes. Generally that happens na. Coarse grain size materials are better for creep as compared to
So,
fine
so
grains.
means like, is there any mechanism of creep where this value of P is equal to zero, like it is independent of the grain size?
P is zero in case of, like, I can give two examples, like viscous glide or dislocation climb. In those, P is zero. Like for Nabarevering creep or Cobble creep, the P is 2 and 3 respectively. For grain boundary sliding creep, the P is 2, but for dislocation climb, it is 0.
Okay, sir.
Okay, so now we'll go to the mechanisms of creep. So one is diffusion based. So in this, all those things like Cobble, Nabarevering, the things come. Second one is dislocation based. So in this we have like power law creep, Whitman's creep, jogged screw dislocation. All these things come in this. Okay, so I'll discuss what is Nabarevering creep. So mainly question and gate comes from these, like what is the grain size relation for Nabarevering Cobble at low temperatures, what is operative, at high temperature, what is operative. So those things will be clear here. So Nabarevering, what happens? Diffusion of vacancies from grain boundary perpendicular to applied stress. Two grain boundaries parallel to applied stress. Through the lattice. So what happens? Diffusion of vacancies occur from grain boundaries that are perpendicular to the applied stress to the grain boundaries that are parallel to the applied stress through the lattice. This is the important point for Nabarevering. So like suppose we have a grain like this. This is the applied stress. So after some time, what will happen? This will elongate like this. So how the diffusion of vacancies occur? So this is the direction of movement of atoms. So the direction of vacancy movement will be just opposite. This is for Navarro herring. In cobalt creep, what happens? Diffusion of vacancies. Same thing, from grain boundary perpendicular to applied stress. Two grain boundaries parallel to applied stress. Through grain boundaries. This is the important point here. Okay, so same thing, just the diffusion occurs through the grain boundaries. Okay, this is for cobalt. So diffusion of vacancies I have written, but here the direction I have shown is diffusion of these directions, that is diffusion of atoms. So if you see vacancy, then that will be just opposite. So what is the strain rate? So you don't have to remember this relation, just know the grain size relationship with that. So for full it is some constant. This is the diffusion constant through lattice. Stress, this is the interaction volume, d square kt. So all you have to remember is strain rate during Navarro herring creep is proportional to 1 by d square. And similar for cobalt creep, it is proportional to 1 by d cube. And this occurs at high temperature. And this is relatively low temperature. Why? Because we know diffusion through lattice require higher activation energy. Because lattice structure is ordered and close packed as compared to grain boundaries. So one important point is when the grain size reduces, then what happens? Fraction of grain boundaries becomes more. So then what happens? When fraction of grain boundary is more, the diffusion to grain boundary will be much easier, then cobalt creep dominates over NH creep. Sorry. So is this clear? Similarly, at low temperature, low temperature favors operation of cobble creep and high temperature favors operation of Nabar herring creep. So what is grain boundary sliding? This is also one mechanism of creep. So this is typically a response of grain boundary, usually high angle grain boundary. To an applied shear stress. So this is supposed to occur by the relative motion of grains along a common boundary or along a narrow zone adjacent to the grain boundary. So one is called grain switching. In this, suppose we have grains like this. And applying stress in this direction. So there will be intermediate stage where this will become something like this. And then there will be final stage where So this is how grain boundary sliding occurs. Another we can say so we're applying stress in this direction. This is the region where there will be stress concentration. So what will this do? This will cause emission of dislocations. So suppose this is our slip plane, then dislocations will be generated and they will move until they reach this boundary. So dislocations move to the front of grain boundary and pile up. And this pile up can be removed relaxed by dislocation climb. So the other mechanism is power law creep. This is an important mechanism, and this is mostly dominated by dislocation climb. And this mechanism is grain size independent. And the stress exponent value varies from 4 to 7 in this. So one model is called Whitman's model. In this what happens? Dislocation glide across large distance followed by climb at the obstacles. Okay, so climb is the main rate determining step. So the creep rate determined by the rate of dislocation climb. Another is there jogged screw dislocation model. So when an edge jog forms in a screw dislocation, okay, so when edge jog is formed in a screw dislocation, the Burgess vector lies out of plane, slip plane, so the edge dislocation part cannot move easily, so climb is required to move the dislocation, and a row of vacancy is formed. To move that jogged part. I hope you know what is kink and jog, all those things. These are just part of dislocation that lies in the plane. Kink and the jog is that lies out of the plane. So it is like this. So this is the Burgess vector, but this is dislocation. This is the screw part. Because the line and Burgess vector are parallel, this is also screw part. This part, this is the edge part, and in this part, the B lies out of the slip plane. So dislocation movement becomes difficult without climb. And when it moves, it will create a row of vacancies. This is the jogged part. So this part, wherever it goes, it will create a row of vacancies like this. Creep. What is important more? Yes, another stacking fault energy you can say. So what is the relation of stacking fault energy with creep life? Can you just think about it? How it affects the creep properties? Okay, so stacking fault energy we know responsible for cross slip. This is an important point, remember. Responsible for cross slip. So what happens? Like we have two partial dislocations. Okay, so this is the width between the dislocations, partial dislocations. So during cross slip, what happens? These two must form a constriction. That means they have to come close together so that they can cross slip. In that case, we have a relation that stacking fault energy is inversely proportional to the distance between them. Okay, if the distance is high, Wait a second. Yes, this is the relation. The distance between them is Gb by 4 pi gamma, and this is the stacking fault energy. So this stacking fault energy, if it is low, this distance will be higher. Okay, I will check this. Wait a minute. So higher the stacking fault energy, lower the width of partial dislocations. This implies that easy constriction formation. So what that means, suppose this is the partial, we call them Shockley partials. So when they have to cross slip, they have to form something like this. At some point they have to be 1, then only cross slip can occur. Okay, so when this width is, this is d, this width, so when this width is d, that is small, that means they can easily form constriction. So for this, what should happen, the stacking fault energy should be higher. So higher stacking fault energy, easy cross slip. So many times they have asked these questions based on stacking fault, how the Easy cross slip or slip depends on stacking fault energy. This is very important point. Lower gamma is difficult cross slip. Okay. So for creep, what do we want? We want difficult slip process, because slip means plastic deformation and easy plastic deformation means easy creep. So what is suitable for creep? Which material? Lower stacking fault material. So if two materials are there, one has high stacking fault energy and the other has low stacking fault energy, then for creep we prefer this material, low stacking fault energy, because in this cross slip will be difficult. So higher creep life. So remember the relationship between the distance, width of the dislocation, two partial dislocations, and the stacking fault energy. This is very important point. And there are some other like one is there Larsell mineral parameter. So what is this? This is an indication of creep life. So that we write P equal to T log T plus C. So just C in liter, it is given properly. This T is the temperature in Romer scale, degree R. This is the creep life or time to rupture. And this is a constant, it is 20. So that will give this temperature T and C. That will ask to find the what is the Larsell Miller parameter for this. So just go through liter once. These all things are given there.
Sir, sometimes this value of C is also given as 46.
So 46 in that case, temperature you can take in Kelvin.
Okay, sir. Okay, sir.
According to that is changed. In liter it is given this relation, T is in Romer scale and C is 20. But in previous gate question one I have seen, there it is given in Kelvin and directly the C you can put 46. That will also work, same result. It's better to remember T in Kelvin and this 46. This is better. Because if you have to convert to Romer scale, then you have to review this UFI F minus 32 by 9 equal to R by 4. You have to convert from C to R, then you can use that. Here you can directly put Kelvin and use 46 as C. Okay, so I'll stop today here.
Sir, will there be further classes in the upcoming week?
There will be classes. Why? What happened?
Sir, like you would be taking this or not? So because according to the schedule, like from the next week, like nothing has been assigned. So
Nothing like the subject what I have to teach, that one that I have filled the Google sheet they sent. They
okay,
have not.
no, means sir, it is showing blank. Like at this that these classes will go on or not, we don't know.
These classes will go on.
Sure, sir. Sure, sir.
Okay.